Hello, my name is Joe Woodworth. I'll be talking about a project we are working on in Google Research called Confidential Neural Computing. We'll start by talking about generative AI and the need for privacy there. Then, we'll discuss some core technologies and how they could combine to address the problem at hand. Finally, we'll talk about some of our ongoing areas of exploration. Let's talk first about private Gen AI. As you've no doubt heard, generative AI applications are on the rise, with models growing more and more capable. There's an increasing demand to integrate these models into products in personalized ways. Personalized Gen AI can adapt to your context and produce personalized results and functionality tailored to your needs. Personalized Gen AI integrations would need to process user data, some of which could be highly sensitive. For example, hypothetical applications may want to use screen content, microphone, chat messages, or any number of sensitive data sources. It's important that such sensitive data should be handled with appropriate safeguards. As an added challenge, today's top generative AI models are large. The number of parameters for these models are often in the billions and trillions. For inference model serving workloads, we serve a pre-computed model. These workloads often have low latency requirements or want to achieve high throughput. For training or fine-tuning workloads, the jobs are typically long-running, iterating over large data sets, executing many resource-intensive computations. All of these requirements mean that computational resources can be a constraining factor. There has been a lot of work and progress recently to get larger workloads to run efficiently on mobile or edge devices. However, for very large models, and especially their associated training workloads, running on device is infeasible due to limited resources. Such intensive workloads are typically delegated to specialized remote server. Running workloads with user data on remote servers adds privacy risk. In this diagram, we show components of a user running a mobile app, which delegates a workload to be run on a cloud platform. Each computation and communication layer introduces risk to the user and their data. Either through malicious action or security vulnerability, the user's data may be leaked, logged, or misused. The app may leak, log, or misuse the user's data, or fail to securely communicate with the cloud platform. We are not focused on mitigating vulnerabilities at the app level. On the cloud platform, threats can come from insiders, for instance, from privileged admins abusing their access, as well as from hackers exploiting vulnerabilities. The cloud platform may reuse the same hardware or host platform for other cloud platform users. Without sufficient isolation, data may be leaked to separate users or separate workloads. We need privacy safeguards to protect against several attack vectors and earn user trust. Our primary objective is to build an infra for the cloud platform to securely perform Gen AI workloads. For the hardware layer, we rely on guarantees from current confidential computing technologies. Next, let's discuss some of the core technical components. Let's talk about some relevant terms, how we'll use them in this talk, and how they relate to each other. When we talk about confidentiality, we mean that information is not made available to unauthorized individuals, entities, or processes. Confidentiality is a property of a system and typically requires various technical mechanisms to enforce. Privacy is closely related to, but distinct from, confidentiality. Privacy is the ability for an individual or group to control their information or data they own and only share it selectively. For instance, only share it with certain systems or parties for limited purposes. So a system which is confidential provides the means for its users to protect their privacy. A confidential system will safeguard the privacy rights of its users. Transparency is when the implementation and execution of a specific process or system is visible to and verifiable by individuals or groups. Transparency can support privacy, or transparency and privacy can be in tension. For example, if transparency is applied too broadly, a service owner may transparently release a proprietary model. This increases transparency of the service while compromising the model owner's privacy. When applied appropriately, the transparency of a system can build trust. For example, a transparent system may allow users to verify that the system uses confidential mechanisms to enforce reasonable privacy requirements. A basic aspect of confidentiality is the goal of data protection. Data is exposed to risk in all states. The best defense is a layered approach that combines protection for every state of data. For data at rest, we typically use encrypted storage, for instance, hardware-based full disk encryption, protecting data even if a device is physically stolen. Additionally, we may apply access controls, implementing strict permission systems. For data in transit, we also use encryption via secure communication channels and network protocols such as TLS, Transport Layer Security. Confidential computing provides protection for data in use. The primary technology we rely on is the Trusted Execution Environment. Trusted Execution Environments, or TEEs, are hardware-based, secure, isolated areas within a device's processor. TEEs are designed to protect data in use, securing data during computation. TEEs function as a sort of reverse sandbox. The code and data inside the TEE is protected from the broader system. In our setting, the TEE helps protect against vulnerabilities or malicious code in the cloud platform from snooping or hijacking the data and code inside the TEE. Specifically, TEEs provide two properties, confidentiality and integrity. For TEE, confidentiality means that the data in the TEE cannot be accessed from outside the TEE, even by the OS. Integrity means that the code running in the TEE cannot be tampered with and runs only as intended. At the hardware level, we make use of confidential CPU-based computing such as AMD SEV SNP and Intel TDX. AMD SEV SNP, Secure Encrypted Virtualization Secure Nested Paging, provides full encryption of a VM's memory with a unique key. It protects against snooping from the hypervisor or other VMs on the same host. Intel TDX, Trusted Domain Extensions, uses isolated VMs called trust domains. It uses new CPU instructions and memory management to enforce isolation and attestation of these trust domains. Support for AMD SEV SNP-based and Intel TDX-based confidential VMs has been announced by multiple cloud providers, including Google Cloud. For large-scale computations, accelerators are critically important. In the confidential computing space, NVIDIA has released the H100 GPU as their first GPU to support confidential compute mode. With confidential compute mode, data moving between the CPU and the H100 GPU is encrypted and decrypted on the fly. This prevents snooping on the PCIe bus, and integrity checks ensure no tampering has occurred. Confidential compute mode separates the T within the GPU via hardware firewalls. With confidential compute mode enabled, data on the GPU is inaccessible from the host CPU, operating system, and hypervisor, even during data processing. It should be noted that confidential compute mode's encryption, decryption, and added security measures have some performance impact compared with running computations on H100 without confidentiality enabled. Recently, H100s have been in high demand for their high performance at GenAI training tasks. The cost and availability of H100s motivates exploring alternative accelerators. For instance, we have done some investigation into Intel AMX CPU-based acceleration as a cheaper, more widely available alternative. Intel AMX Advanced Matrix Extensions is specifically designed to speed up matrix multiplication as a key step for deep learning tasks. A key part of applying these confidential computing technologies is remote attestation. Users, either clients of a cloud platform or end users, want to be able to verify what the workload processing their data is doing. One requirement of remote attestation is to follow a transparent release process, which yields reproducible, externally verifiable builds of the T container workload. Remote attestation has three key components: an attester, a verifier, and a relying party. In our setting, the attester would be the remote machine that we want to verify. In response to a challenge from the verifier, the attester responds by securely communicating evidence. The evidence is a cryptographic confirmation of the computing environment's state. It includes information about the processor, the firmware, and the software running in the container, which is signed by our hardware root of trust. The verifier's role is to challenge the attester, to store a database of known good measurements called reference values, and to do a comparison between the attester's evidence and the reference values. This comparison is communicated to the relying party via an attestation report. In our setting, the relying party may be a mobile client. The mobile client wants to determine if the expected transparent release build is running on the remote machine on expected hardware. The relying party trusts the verifier, which provides an attestation report, and only sends the remote machine requests and data if the attestation report matches the client's requirements. So, to summarize the goal of the confidential neural computing project, we are an exploratory research effort that is working to build an ML framework that enables generative AI training and inference in secure enclaves. Our framework targets trusted execution environments. It leverages confidential CPU and confidential accelerators. It's built for remote attestation. It supports privacy via confidentiality and transparency. This diagram illustrates how some of the components work together to perform inference. The service owner initializes the service. As part of the initialization, the service loads the T container into the guest VM, and the service owner provides the model to the T container via an encrypted channel. With the service initialized, the mobile client can request attestation evidence for the container running in the remote machine via the verifier. Once the evidence is verified, the mobile client can start sending encrypted requests to the container over a secure channel. The requests are decrypted inside the T, then fed to the model runtime for inference, and encrypted responses are sent back to the mobile client. The requests and responses are only visible to the mobile client and inside the T, not in any intermediary layers running on the host machine or cloud platform. It's also an option to incorporate additional sources of user data. Such additional data access would also need to handle key management and attestation, similar to the mobile client. Without this additional persistent user data, the service would be stateless, responding only to information present in each request. But adding persistent user data would allow it to be stateful. Next, this diagram illustrates some of the components for training. The service owner initializes the service, acting through a differential privacy layer. We'll talk more about the purpose and mechanisms of differential privacy on the next slide. The differential privacy layer may load multiple T containers on multiple VMs. Each T container is attestable to clients. In addition to loading the base model, the service owner also receives model updates from training. Model updates are based on training steps that process training data from a group of users. Differential privacy logic controls the access of user data in the group, and the training steps may be separated into multiple T containers, sliced to isolate user data and ensure privacy guarantees. At a high level, differential privacy is meant to help the model learn from realistic samples of user data without learning individual private information. Differential privacy prevents this by introducing controlled noise into data sets. Appropriate privacy guarantees can be made through adjusting noise based on epsilon and delta values. In differential privacy, epsilon represents the privacy loss budget. Smaller epsilon represents more privacy. Delta provides an upper bound on the failure probability. For large delta values, the epsilon privacy guarantee is unlikely to hold. Differential privacy comes with limitations. There's a trade-off between privacy and accuracy. High levels of privacy require high levels of noise. Data with high added noise are a less accurate representation of the real population and may be less useful for modeling. Additionally, applying differential privacy to model training typically incurs additional computational costs. This is especially important with the scale and costs associated with Gen AI models. Next, I'll talk about some of our ongoing areas of exploration. A foundational requirement of our approach is to get these Gen AI workloads running efficiently in T-based environments. We continue to benchmark and optimize performance of Gen AI models on confidential H100 GPU and Intel AMX. And longer term, we seek to prove out feasibility and performance for multi-GPU and multi-node environments. We also continue to explore alternative T-based confidential frameworks, such as confidential VMs or confidential space from Google Cloud, as well as integrations with Project Oak to different cloud platforms or on-prem solutions. These frameworks have different requirements and capabilities and offer different levels of confidentiality guarantees. We expect that different framework configurations may be suitable for different clients. Beyond just getting these models to run efficiently in confidential environments, we are also developing a general-purpose ML infrastructure that clients may integrate with to enable confidentiality for their Gen AI inference and training workloads. The infrastructure will provide tools to enable attestation of the workloads and end-to-end encrypted communication between the model service and client. This infra will protect the use of private closed-source models, which may be proprietary and should not be made publicly visible. We plan to open source the container code run in the T for remote attestation and external verifiability, but want to keep proprietary models private. The public open source infra will dynamically load the private model via an encrypted channel. The infra can impose constraints on the dynamically loaded model. For instance, the infra can impose that operations adhere to specified differential privacy requirements. The infra will support integration with differential privacy components, making use of accelerators in T to efficiently run workloads. The goal is for the infra to support building confidential computing components that fit into a client's larger ML training pipeline and provide private data protections for their users. Such protections must be evaluated at the ML pipeline level to understand the benefits of the Ts for the system as a whole. If you'd like to learn more, please contact us at projectcncteam@google.com. Thank you.